Okay, so here, this is homework 2. And the topic is, as I mentioned last time, in implementing the naive Bayes email spam filter. And for this, there are 3 exercises. So recall the idea of this naive Bayes email spam filter was that we have a dictionary, which was just a collection of words. And then we encoded an email by writing it as a vector of zeros and ones. And 1 indicated that the word at this position in the dictionary is contained in the email. So for example, here I gave a really simple dictionary. Maybe you can, by yourself, create maybe more interesting dictionaries, but I created one in the list of emails so we can later compare our results. And so here the dictionary contains a few words like hello, students, please learn, and so on. And then I give you also a list of test emails. And by this I mean I give you an array of arrays. So here, I don't know how many emails I have, but each email has a text. And then it indicates if this is spam or not spam. Yeah, so maybe really let's just do it slowly. So let me run this. Oops. So here, for example, I can check test emails. The first entry, this will give me this entry here. And if I want to actually get the text of this email, again, take the first entry of this. So this will give me the email of the first data set here. And the second entry then will tell me if this is spam or not spam. So in this case, this will give me a 0. And your first task is it to convert these emails into a feature vector. So in our example, we had this feature space X, which was given by these vectors of zeros and ones, where D is the size of the dictionary. And the first exercise here is to actually convert such an email into a vector. So you should write a function here, which we denote by email to feature, where you give as an input the dictionary, and you also input a text. So maybe, I don't know how much I should say, but for this you will need to look up some functions in Python. So for example, let's do an example. Let's take an email and say, hello, today is the lecture. You. So this is an email, but also in this email there are some words which are not in the dictionary, but let's not care about this. And for example, I now want to convert this into a vector. So let's maybe first check how many words we have in the dictionary. I think it should give me the... Oh. So in our dictionary we have 39 words. So what we want to write is a function which converts this string here into a vector of size 39, which zeros and ones. And for this, what you would need to do is you would need to go through the dictionary and check for each word in the dictionary if this word is contained in the string or not. So maybe for some of you this is now really boring, but maybe also some are not so familiar. So I want to do it slowly. So maybe let's go like this. So this will now go from 0 to 38. And for example, if we would just print dictionary at this position J, then this will just now give a list of the words in the dictionary. But for example, in this example here, we want to check if this word, for example, is contained in email. So what we can do to check this in Python, it's quite simple. So we can ask if, and then this is now the word at the position J in this dictionary, and we can just ask in email. So this here will just check if this word is contained actually in this string. And then we can say, for example, in this case, so what this will now do is it goes through the dictionary and checks if this word is contained in this string here. And then we see from these 39 words, we have hello is contained, the today is how are you in this email. And similar for this homework here, to write this function, you will get an email like this text here, and you give this a dictionary, and you should return a vector. So maybe you will just start with a vector, which is just zeros everywhere. And then depending if this statement here is true or not, you will put a 1 there on. And this second function here, what you should do there is you should convert these test emails, which are given by these arrays of arrays, into a new array of arrays, where instead of having the text in the first entry, you will have this feature vector. So this then should correspond really to what we call a training set, an array of tuples where the first entry is really an element in our feature space. But if you implemented the first function, I think the second function is clear, hopefully. And then the main task of this homework is to implement this algorithm we described in the lecture. So for this, we introduce these phi's. So these phi's here, I denoted in the lecture with a phi tilde, because this tilde meant that I use this Laplace smoothing, but here I just called them phi. So if you compare it to the lecture notes, maybe the only difference will be that there are no tildes here. And they can be calculated completely out of these training sets. So these two are arrays of size d, and this here is just the number. And then having these numbers, so this is what we learn by the training. Then getting a new email means someone sends us a text. Then this text we can convert into a vector by using the function in exercise 1. And then for this vector, we can calculate these probabilities. So these are all 4 possible cases for this probability. Either the word is contained, or it's spam, and so on. So we have all 4 possibilities here, and these can be calculated by using these phi's, which you now, if you implemented them at this point, you can use them. There's a question in the training set, the n and xn. Yes, so this n here is the number of trainings emails. So actually, in our case here, n would be the length of this test emails. In our case, this n is 14. So because we have 14 emails here, and for each email we have a feature vector, and for each email we have 0 or 1, depending on if this is spam or not. But these numbers, these phi's, you calculate for each word. So these phi's, this and this will both will be an array of size, in this case 39. But this n here and the sum, this is the sum over these 14 training email. Okay, and then having these numbers, you get a new email, meaning you have a new vector x, and then you can calculate this probability here, px, given y, which is a product of these p's, which can be calculated by these phi's. And therefore, you can calculate this expression here, which says that given a new email x as a vector, what is the probability that this is spam? So this formula we introduced in the lecture, and then you need to calculate this expression here, which is, so this expression here just uses these numbers here. So if you solve exercise 2, so exercise 2 is to implement a function for this here, namely what you want in the end is a function which gets an email as a text, and then it should return a percentage of this email being spam. And maybe you don't want to put everything into this thing here. So maybe at this point before, maybe you just start creating your arrays for the phi's, and then maybe write a function to evaluate this thing here, and so on, and then do it step by step. And then in the end, maybe in this function, you will just implement this final formula here. But yeah, we didn't want to give a lot of restriction here, so you can implement it however you want. So maybe some of you will do it much better than I did it in the solution I wrote. Yeah, and then, so there's a small typo here because we changed the name. So in the end, you should all check, so we can compare it later, what the spam percentage for this email here is given this training starter and this dictionary here. And then I hope we get all the same percentage for this email. And I think the percentage that this is in spam email is quite high, but here this function should be this function, so don't be confused. So this is what you should execute in the end, and then this gives a number, and this helps us to compare with your solution. And then in the end, like a bonus exercise, maybe for those where the first part is a little bit boring. I mean, maybe some of you can extend it a little bit in a way. And one way to extend it, for example, is to create a dictionary out of emails. So instead of writing a dictionary, maybe you just get a list of emails, and then you go through each email and collect the words. But then you need to take care that you don't collect them twice. Because, for example, here, if I go through these emails and create a dictionary, I need to be careful that I don't put hello 6 or 5 times into this dictionary. But maybe some of you have even nice ideas to extend the spam filter. Are there any questions on this? So maybe tomorrow in the study session, you can go through this together. And especially those maybe who don't have any Python experience, I hope this is a good start, because I think you don't need a lot of Python here. You just need to know how to use a for loop, go through some arrays, and need to know things like this, that you can check if a word is contained in another. If a string is contained in another string, you can just use this word in here. Yeah. Okay, so if there are no questions, then I would stop sharing this. So the question, when is deadline? I think we did a 3 weeks deadline, but I think there's not really a deadline in the class. So there's an official deadline in the classroom, but I think we can still access your solutions afterwards also. So we still didn't really figure it out how to use GitHub Classrooms. But maybe just try to do it before Christmas, and then that's fine. Okay. Okay, so today I want to continue on these support vector machines. But actually, I needed to give a Japanese talk today, so I didn't have much time to prepare this lecture. So I will maybe do a lot of handwriting today. But let's recall what we did last time a little bit. What was the main idea of these support vector machines. So the rough idea was that we want to separate certain data sets. So the feature space will be something in RD, where D is the number of features. For example, in this picture here, D equals 2. And the label space will be again -1 or 1, or similar to the spam filter where it was 0 and 1, but in our case we want it to be -1 and 1. But again, it's an example of a binary classification problem. And what we want to do is, in the first step of this thing, we want to separate these data points by a line. But of course, in real-life application, the data points will not look nicely like this. They will look quite complicated, but still there will be the so-called kernel trick, where we will view them in a higher dimensional space. And in this higher dimensional space, we can maybe separate them by a hyperplane. And yeah, but today we will still talk about how to solve this simple case here. And for this, we recall some linear algebra, namely the dot product, because with the dot product, we are able to describe such a hyperplane. And so what the dot product of two vectors was just given by, so if I have two vectors, let's say, maybe let's write it directly with the, so if I have a dot product of A and B, this is just A transpose times B, and it has some geometric interpretation, namely if the length of B is 1, then the dot product is exactly the length of this part here. And then we saw that if I have a vector B, and I consider, for example, all vectors A such that the dot product is fixed, then I consider all points on this line here, and this gives us the possibility to describe a line by using this dot product. Yes. So in general, if we use this vector W, which was the normal vector on the plane, and we had this number B, which in some sense corresponds to the distance of this plane to 0, and which is exactly the distance if this W has length 1. And then we defined this hyperplane HWB, which is exactly given by all vectors in RD, which satisfy this equality here. So again, in picture, we have some W, then HWB is a plane which is where this W is orthogonal to. And this B is basically this part if the length of this W is 1. If this is not 1, then we can divide by the norm of W, and then this length here is B divided by W. So therefore, this length in general is always B divided by the length of W. Okay. Are there general questions about this form here? Okay. So then the goal we want is we want to find a W and B given some training set. And then, so we had this example here. But in the end, we then saw that we want to solve the following problem. So here we have a training set with two labels. Blue corresponds to 1 and green corresponds to -1. And what we wanted to fix is that the points which somehow are closest to our goal hyperplane, that they satisfy the equation that this dot product here of W with this X minus B equals 1, and similar to this. And this here we called the functional margin. And then doing this, we saw that the distance here between these two lines is exactly 2 divided by the length of W. And what is the perfect hyperplane in our example, where the perfect hyperplane is the one where this distance here is maximal. So we want to maximize this 2 over W, and therefore we want to minimize this W with the condition that this functional margin of all these points is greater or equal to 1. Because these points here on this side, oh, green is bad. Here on this side, they satisfy all the condition that the dot product here is greater or equal to 1. And on the other side, they satisfy that this is a smaller or equal to 1. And then if we multiply with the label, which on this side is +1 and on this side is -1, then we get the equation that this here, the label times this thing here, so the functional margin should be greater or equal to 1. Because this exactly means that there's no point here in this thing here. So that really the plane here is between the nearest points of these two classes. Okay, and so goal is to solve this problem here. And this is an example of a so-called optimization problem with linear constraints. And we want to rewrite this a little bit. So maybe let me copy this here. And just to make sure that this is actually the same, but just written down in a different way. So still we want to find we want to find W and B. But we want to minimize 1/2 of the norm squared. But actually this is not really a difference, because if we minimize 1/2 squared, then this is exactly the same as minimizing just the norm. And the only reason is that here we have some square root in the definition of the norm, but we don't care about the square root, and it's easier to just work with this here. Because here, and the 1/2 we will see, because we will take the derivative with respect to W, and then this 2 will go in front, and then it's easier to write down. So here, just to make sure, the norm squared is exactly just W times W. Oh. So in other words, if the entries are W1 up to WD, then this here is just really the sum of the squares of the entries of W. So this is here the part of what we want to find the optimal value for this W. And then we have so-called linear constraints. Namely, we don't just want to find the minimum of this. This would be quite easy, actually. But we want to find the minimum in such a way that we also have this condition here. And here, this is just really, oh. Oh. Oh, sorry, I want a sign change here. But this doesn't really matter, because here I changed the order. But this is exactly this equation here, by just bringing everything on one side. So in other words, we just want to find W such that this F here is minimal, with the constraints that these function J are smaller equal to 0. Okay, and this is what is called the linear constraints, because this here is a linear function in W. Because these W we are just multiplying with some x, and the x can be seen as some constants because they are our training examples. Yeah, again here, so this n is again the number of training examples, the number of points, and here this xj is the feature vector, so this is the position of the point, and this yj is just plus or minus 1. Okay, and so how does such a problem look like? So this function here is something quadratic in W. So here we have a sum of squares. So for example, let's consider the case d equals 2, for example. Then the graph of this thing here would be, for example, W1 squared plus W2 squared. And for example, this could look something like this if we would draw this and maybe have here W1 and maybe W2. And if we would just need to minimize this function here, then we see in the picture, well, then there's just exactly one point. And this point we could maybe find by just taking the derivative with respect to W1 and W2. But now we also have these linear constraints, and I want to draw now how this looks like if we have linear constraints, because then maybe this point here doesn't satisfy these linear constraints. But first, I want to draw this a little bit differently. So maybe let's consider we look from top onto this thing here. So maybe now there's W1 and W2. And now for different values of this function, we can draw a line. So for example, let's say this is here the value. So maybe let's say here we have fw equals 1. And maybe here we have fw equals 2. And so on. Okay. And here, for example, in the middle, we have the minimum in this case. It's really simple because it's just 0. But now, how do linear constraints look like in this picture? So what could be an example for a linear constraint in this W? For example, one linear constraint could be 2 times W plus W1 plus W2, maybe smaller equals 0. So this is a linear constraint in W1 and W2. And so let's see how this looks in this picture. So this constraint here, I mean, we can write this as W2 smaller equal minus 2W1. So this is somehow, if you think of y and x, this is just a line with which looks like this maybe. And smaller means that this is a part on this side here. Yeah. So therefore, where this picture still with the linear constraint, we also have this point here. But maybe let's do also another linear constraint. Let's say, maybe let's do it easy. So for example, this here, is also a linear constraint. And this just means that W2 is greater or equal to 2. So we have this constraint here. So somehow we are just allowed to find something here on top. So now, if we want to minimize this together with these two constraints, then the optimal solution in this picture is where? Well, we know the value of f. The more we go into the center here, it gets smaller. But here in this area, we are not allowed to go, because in this area, we do not satisfy these equations. So therefore, we need to find the point which is in these two areas. So the only area where we can look for a solution is this part here, because this part satisfies both constraints. And the part in this area with the smallest value of f is exactly this point here. So in this case, if I did everything correctly, I hope, this is a solution for W, because this point satisfies these two conditions, and it also minimizes this function f. Okay, and this is an example of an optimization problem with linear constraints. So and now how to deal with this in general. So to solve such a problem, one considers so-called Lagrange multipliers. And so maybe let me copy again the problem we want to solve with the typo here. So we have here our problem. And now what we define is this function here. Oh, I think here I also want a plus. Sorry. And now let's consider the following. Namely, so what we did here is we have the function f, which we want to minimize. And here we have this function j. So for each training example, we have this constraint. And we have these Lagrange multipliers alpha, which are now some numbers, which in our case will be positive. So they all will be positive. And let's see why we want to consider this thing. So for this, first we define theta p. So this p here stands for primal, because this here is the so-called primal problem, or primal constraints. Primal. And what I want to define is now theta p of w, which is maximum over all alpha, where these alpha 1 up to alpha n is greater or equal to 0, of this Lagrange function w b alpha. Yeah, so I fix, oh, sorry, here I should write also b. So I fix, for a fixed w and b, I want to consider the maximum value of this Lagrangian over all possible alphas. And now assume that So if I have a W and a B, which do not satisfy this constraints here, so if one of these G's is positive, this would mean that one of these, so let me write this down. So if for one J, we have that this G W is actually greater than 0, then this would mean that I can make this here arbitrarily large, because then if this number here is positive, then of course I can make this sum here infinitely large by just increasing this alpha j in this case. So in this case, this theta p WB is just is infinitely large. Yeah. But if this is not the case, if all these, if for a fixed W and a fixed B, all these G's are negative, then the maximum value of this thing here is exactly the FW. Because then if all these numbers are smaller or equal to 0, then the maximum value of this thing here is obtained by taking all alphas to be 0. Because otherwise, if alpha is not 0, then I would subtract something from this value here and would make it smaller. So therefore, this maximum here is obtained by considering all the cases when these alphas are 0. So therefore, what we get actually is that this this thing here is f of W if W, let's say, satisfy all constraints, and otherwise it's infinity. Yeah, is this clear? So therefore still so what we want to find now is, so we want to find the minimal value of this guy here, because the minimal value of this will give us the minimal value of FW, and these constraints are satisfied. Because if a constraint is not satisfied, then it explodes anyway, so it's infinity. But if it's not infinity, and if it's minimal, then we get the minimal value for F. Okay, so let me add a page here. So what we want is minimize over all W and B. We want to minimize this theta P W B. Yeah, so we want to find the W and B such that it's minimal, because if it's not infinity, then this WB satisfies these constraints. And if it's minimal, this also means that the value of FW is minimal. And therefore, I mean, what was the definition of this theta P? So here we want to minimize WB of, and here the definition was we want the minimum of the maximum of this Lagrangian. Yeah. Okay, and now the main idea here is that we will change this order here of minimum and maximum, and there are arguments you can bring to show that in the end you will actually obtain the same results. So in general, this is not the case if you have a minimum of maximum of something, that you can just change the order of minimum or maximum. But one can show that in this case, this actually works. And then the problem we will obtain is a so-called a dual problem of our optimization problem. So, so what we will define is theta d for the dual problem. And now this will be a function on alpha. And this will be given by the minimum over all W and B of this Lagrangian. And the statement is one can show that the minimum oops. Yeah, so now the maximum over these alphas of this dual problem is exactly will give the same value here. Okay. So what we want to do now is we want to calculate this here. And then in the end, we want to solve the dual problem by finding the maximum of this explicit thing here. Yeah, so it maybe sounds strange, but we will later see that that this will be helpful when we consider these kernels. But first, are there any questions so far? Maybe some parts are confusing. Oh, and I see I should charge my other iPad. Otherwise, I cannot see your questions soon. Anyway, let's do this. So this is now the so-called dual problem. So so again, so we want to consider this one here. So we want to maximize this theta dual of alpha, which is given by the minimum of this here over all W and B. And so what was this in our case? This Lagrangian, this was given by this function here. And maybe let me also copy the function g here. So oops. Okay, so I hope you can see this. Maybe it's a little bit small. So maybe let's plug everything in. So here we have 1/2 the WTW, or maybe let's write directly the, yeah, let's write it WTW minus, and here we have the sum, j goes from 1 to n, alpha j, and here we have the y j w t x maybe here x j plus b minus 1. Yeah. And oops, and everywhere here there should be a minimum. Sorry. So we want to minimize. So maybe just okay. Is this okay? So this is now plugging in the f here, and here for each j I plugged in the, so here's now minus j of w, and we want to minimize this. So for a fixed alpha, we want to minimize this with respect to w and b. So how do I minimize this? Well, this is now just a quadratic function in w and b. So what you just want to do is we want to just take the derivative and set it 0, because this here really corresponds to a graph which looks like this here. And we don't have any constraints. We just want to minimize this. So we really just want to find this point in this case here. And what we can do for this is just take the derivatives with respect to w and with respect to b. And by this, I mean we take, because these are vectors, we just take component-wise the derivatives of this function. So we take the gradient with respect to w of this, and then we want to set it 0. But first, let's calculate this. So don't be scared now. So these are all vectors. Oh, sorry. So this is just, this is just a number depending on w. And so yes. So this here just means now we take the derivative with respect to all w's. So this term here, which is just a how to say? I mean, this is just we take the derivative with respect to w1 up to wd. And this vector here is, or this number here is just the sum of the squares. So if I have the sum of the squares and I take the derivatives with respect to w1 with 1/2 here, I will just get w1. If I take the derivative with respect to w2, then I just get w2. So this here will be a vector where in the first entry I have w1 of this, then w2 up to wn. So the vector I get is just w. And here, so now here we need to check what we get if we take the, so first of all, this part here doesn't depend on W, so this just vanishes. And here we take the, and each component here, the derivative with respect to W. So what we just get is, we just get the entries of the vector X. So here we get just the sum, AJ. So this Y is just a number. And here, maybe let me write this down to make it clear. So this here just means W1, xj1 plus W2, x1, xj2 up to W d x dj. And if I in the ith component take the derivative with respect to wi, then I just get the ith component of this vector xj. And therefore the vector I have here is just the vector xj. Yeah? Is this clear? And what we want to do now is, so this is the derivative with respect to W. And we also take now the derivative with respect to B, which in this case is really just a number. And the only part depending on B here is this part. And therefore, this is just the sum. Oops. Oh, it's minus the sum. From this. Yeah. Okay. So let me copy this. And oops. And recall what we actually want. So we want to calculate this guy here, which is given by the minimum of this Lagrangian. And this Lagrangian is a quadratic function in this W and B, which is in the simplest case, like in the picture. So therefore, to find the minimum, we just want to set the derivative to 0. So we want that these two equations equal to 0. And the solution of this will give us the minimum of this function here. So so we have this here, and to get, we consider that the derivative with respect to W of this is 0, and also this here. So in particular, what this then means is if this here equals 0, this just means that this best W to solve this is given by this sum here, alpha j, yj, xj. And this here just means that this sum here, j from 1 to n, alpha j, yj equals 0. Yeah? So we get this explicit W here as a linear combination of these xj. And this we then want to plug in into this Lagrangian to get this theta d alpha. So let's plug this in. So let me get the definition again here. So, oh, my Menti monitor died. Wait a second. I cannot access the Menti. So if you have a question, maybe please write in the Zoom chat. I'm sorry. Okay, so now let's plug this the value for W into this this thing here. So the W is given by this linear combination here. So this will get confusing now, but so let me check with the yes. Yeah, so let me plug this in here. So we have this part transpose. So this transpose times this. I'm sorry if this is much calculation, but I want to get to one point in the end, which really is important for the next lecture. And then here we still have this sum here. And j goes from 1 to n. And j. And now we need to plug in the w, but now we need to be a little bit careful because of the naming here, because we need different variable name here. So let this be an I, because we have a double sum here. So this we plug there in, also with the transpose times x j plus this b, and there's a minus, so this is a minus b times the sum j goes from 1 to n alpha j. So this now comes from this, so there's also still y j, and minus this part here, minus the sum j goes from 1 to n alpha j. Okay, and now first thing we see that this condition here, that this equals 0, will actually simplify something here. Namely, this will simplify this term here. So actually, there will be no b anymore in this equation here. And yes, and now we can also write this out. Namely, yeah, we see that these two sums, oops, are actually the same. If you look at this, and here is 1/2 and here is -1. So actually in the end, this will be, but I have a different sign here. Oh, sorry, so this here is a plus. This is a plus because it's a minus and minus. So the end result is we have the sum of the alphas minus 1/2 and then this sum here. So this is the same as this, because taking the transpose here just means, I mean, these are numbers, so the transpose of this linear combination of vectors is just the transpose of this here, similar to this. And then in both cases, we have the double sum. So maybe it becomes clearer if I just also rename this here I, which is in this case doesn't change anything. But in the end, I have the sum 1/2 I and j go from 1 to n. Then I have the product of these two alphas, and I have the product of these two y's. And in the end, I have the product of x I t times x j. Or in other words, what I have here is xi, the dot product with x j. Okay, and this is the goal where I wanted to go. So this is now the Lagrangian here. And what we want to do is we want to maximize this because in the end, we want to maximize this dual, this theta d. So we already calculated this part here. So we minimized this thing here with respect to w and b by taking the derivative and setting it to 0. This gave some conditions on this w. So now this, or here, so then I should also really write maybe the minimum here. The minimum over w and b, because then here we use, at this point, we use that the derivative equals 0. And therefore this, in the end, is what we here call this theta d. So the dual theta depending on alpha. And the nice thing is that this function here now just depends on the dot product of these feature vectors. And so next time we will see how to, so the goal is to maximize now this thing here with respect to alpha. But later, as I said, we want to use this so-called kernel trick and go into higher dimensions. And the idea of this was to send these vectors, which are in RD, to maybe a higher dimensional space. But the key idea behind this is that we will actually not calculate this image of these vectors in the higher dimensional space. The only thing we will be interested in is how the dot product of these feature vectors in this higher dimensional space will look like. And this will exactly be the kernel in the end. So we really just need to know in the end the dot product of our feature vectors in the higher dimensional space. So maybe to make this clear again, let me copy a slide from the last lecture. This one here. Let me copy this and put it into the. So here, oh, well, maybe this again. So we start here in this case with our feature vectors in RD, but here we cannot separate them. But now we learned here to separate something in some dimensions, we need to maximize this function here, and this function will actually just depend on the dot product of our input vectors. But it will not really depend on the actual vector. So what we will, so actually this word here is not quite correct. So we will consider some phi, maybe from phi RD to phi to R, I don't know, M, where M is maybe really, really big. So it's much larger than D. And in Rm, we can separate these things by a hyperplane, but actually we will not be interested in the value of our vectors in this space. We will just be interested in the dot product of phi of, let's say, some input vector with phi another input vector. And this will then in the end be the kernel. So actually we will not calculate this map explicitly. We will just be interested in calculating the dot product of two input vectors in the space here. But maybe this we will do in detail next time. But the only formula I wanted to show here is this, that in the end we are really interested just in the dot product of two feature vectors and not in the actual coordinates of this vector. So we will actually not be interested in the coordinates here in this higher dimension. We will just be interested in, if I take 2 points here, we will be interested in what is the dot product of these 2 points. Okay, and I think this is enough for today. And maybe one thing I think I wrote it, but I didn't mention it. That in general, these problems like this, so where you want to minimize a quadratic function like this with a constraint like this, so there are really fast implementation to solve these kinds of problems, and this is called quadratic programming. So there are a lot of implementation, for example, for Python to solve such an equation like this. So if you're already at this point here, we can already use some implementation for this. And also the problem we get here in the end will also be such a problem. But yeah, so maybe this I will do more precisely next time.